Here we go. Proving events are independent. Welcome to sixth period, Mr. Myers' class. I know you didn't get a head start on this like my classes did, but let me talk through this just a little bit. We're going to be talking about independent versus dependent situations. So the assignment we did in class today with the rain and the umbrellas, that was an example of dependent events, because depending on whether it rained or not, you had a different probability for whether you would have an umbrella or not. So those events were dependent on each other. So now we're going to be looking at events that are independent. So an example of independent events are flipping a coin. When you flip a coin, if I flip this, it's red. If I flip it again, does it know it was just red? Does it say, oh, now I need to be yellow? No, it doesn't. Look, it even gave me a red again. It doesn't care what happened before. Okay, so those are two independent events. Each time I flip a coin, each event is independent of the one that came before. It doesn't care. It doesn't know. It doesn't keep track of it. Okay. So the coin does not know what the previous flip was, and it cannot affect the next flip. Look what happens when we apply the conditional probability. So we're going to get to this. We're going to apply the conditional probability. But first, let's look at the situation by drawing a table. So here we have a table of the possible outcomes. On the first flip, I could get heads or tails, and on the second flip, I could get heads or tails. So my possible outcomes is I could do heads, heads, or I could have heads, tails, or I could have tails, heads, or I could have tails, tails. And I've listed out my four possible outcomes. Okay, find the probability that the first coin flip was heads, we'll call that event A, given that the second coin flip was heads, we'll call that event B. So we already know that the second flip was heads. So here's my second flip. We're just going to be looking at the situations where the second flip was heads. That's these two outcomes right here. So I'm looking at two possible outcomes, so that's why I have a 2 in the denominator. And I care about the one where the first coin flip was heads. So right here, that's this outcome, so it's 1 over 2. So notice, I just did a conditional probability question. I asked, what is the probability of flipping heads on the first coin, given that I had already flipped heads on the second flip? And it ends up being 1 out of 2. Well, that happens to be the same probability of just flipping a coin all by itself. The probability of just flipping the first coin and getting heads is also 1 out of 2. Okay, so we're going to look at this a little more in depth, and you'll see it happen. You'll see what happens when we use the conditional probability formula. All right, so we need to take apart our conditional probability formula and find some numbers here. So what's the probability of having heads on both coins? So the probability of heads and heads. So that's right here. That happens once out of 4 outcomes. So there it is, 1 out of 4. Now, what's the probability of getting heads on the second coin? Okay, the probability of event B is heads on the second coin. So I'm looking at my second coin here and getting heads. It's right there and right there. So there's 2 out of the 4 possible outcomes, and that can reduce to 1/2. Okay, so now we're going to go ahead and substitute these into our formula and see what happens. So the probability of A given B is equal to 1/4 divided by 1/2. And if we do that, we get 1/4 divided by 1/2. It's always good to rewrite it with a division symbol. Now, how do we divide fractions? We changed it to multiplying by the reciprocal, and that gives us, we can reduce that. That gives us 1/2. So notice the probability of flipping heads, given that the second coin is heads, is just 1/2. Now, what is the probability of flipping a coin and getting heads just on the first coin? So just event A. What's the probability of event A? Well, if we just flip a coin, the probability of getting heads is 1 out of 2. So what we can see then is the probability of flipping heads on the first coin is exactly the same as flipping heads on the first coin, given that we've already flipped heads on the second coin, given that we know we've got heads on the second coin. They are equal to each other. Okay, that did not happen in our umbrella and rain situation. That did not happen. The probability that I would be, that it would have rained, given that I've been carrying an umbrella, was not the same as the probability that it rained. Okay, so that you get different things happening, whether they're dependent or independent events. So notice the probability of flipping heads on the first coin, given that you flipped heads on the second coin. that's this right here, it's just the same as flipping heads on the first coin. They are equal to each other. So therefore, the probability of two independent events happening follows the following rule. Okay, let me look at my notes so I don't mess this up. All right, so we have the probability of A given B is equal to the probability of A and B divided by the probability of B. That is our formula. But we know that the probability of A given B for independent events happens to be the same as just the probability of A. So I'm going to replace this right here. I'm going to substitute in probability of A. Okay, so I can change this to probability of A. They equal the same thing. So the probability of A is equal to the probability of A and B divided by the probability of B. And then we can rearrange this. We can multiply both sides by the probability of B, and we get the probability of A times the probability of B is equal to the probability of A and B. So if events are independent of each other, you can simplify the conditional probability rule to just saying that the probability of A times the probability of B is equal to the probability of A and B happening. Okay? So this is only for independent events. So now we're going to look at dependent events, and you're going to see that this formula doesn't work, falls apart. Okay, so moving on to the other side. Dependent cases. So we already talked about the umbrella and the rain being an example of dependent cases. Oops, somebody's making an announcement. But now we're going to look at a slightly different situation. We're going to be looking at, we have a bag of marbles. We've looked at marble bags before. And we're going to be pulling out two marbles, one right after the other. These events are going to be dependent because if we take out the first marble, it changes the number of marbles in the bag, which then affects the probability of the second draw. So imagine we have a bag with two red marbles and one blue marble. Find the probability of drawing a red marble and a blue marble. Okay, so the red marble is going to be event A. Somehow I didn't get that in here. So the red marble is going to be event A. The blue marble is going to be event B. So we're going to draw, first of all, we're going to draw a tree diagram. So for the first draw, I could get a red, or I could get a blue. Now, if I've already pulled a red, so here's my first draw. If I've already pulled a red out, now there's only two marbles left in the bag. So for my second draw, there's still a red in there, and there's also a blue in there. So here's my second draw. And again, if I've already pulled out a red one, well, there's still a red one, and there's still that blue one in there. But if I've already pulled out the blue marble, then there's a red and a red. Okay, so our possible outcomes are red, 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 blue, red, 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 blue, blue, red, and blue, red. These are our possible outcomes, okay, with this one being the first draw, and this one over here being the second draw. All right, so look what happens when we try, oh, sorry, let's fill this in. I was starting to look at the next part. Okay, what's the probability of A and B? So getting a red marble and a blue marble. What's the probability of getting a red marble and a blue marble? Well, we have 1, 2, 3, 4, 5, 6 possible outcomes. And how many of those are a red and a blue? So red on the first and a blue on the second. Okay, so red on the first and the blue on the second. So if I'm looking at this one right here, probability of red on the first one and blue on the second. Red on the first, blue on the second. That happens twice. So 2 out of 6. And then what is the probability of getting, oh, you know what? I have the wrong notes here, I think. Shoot. Looking at my notes and they don't match up with what I'm doing right now. Okay, what's the probability of getting a red marble given that I've already pulled a blue marble? Okay, so I'm only going to look at the situations where I have a blue marble, so on the second draw. So that would be here I have a blue marble on the second draw, and here I have a blue marble on the second draw. So what's the probability that I would get a red marble on the first draw, given that I've already drawn a blue marble on the second draw? So I have 2 possible outcomes. And how many of them give me a red on the first one? Well, actually both of them. Well, that's kind of crazy. So I have 100% chance of that happening. Okay, that's equal to 1. So now let's try it with the rule for independent events. What happens if I do this with the rule for independent events? So the probability of getting A and B is equal to the probability of A times the probability of B. So the probability of drawing a red marble is 2 out of 3, because there's 2 red marbles out of a total of 3. And the probability of drawing a blue marble, okay, this one right here, is going to be 1 out of 3. There's 1 blue out of 3 marbles. So if we think about just the basic probabilities, the probability of A and the probability of B, so I have the probability of A is equal to 2 over 3, and the probability of B is equal to 1 over 3. Now, if these were independent, then when I multiply these together, it should give me the probability of both of these things happening. So if I do 2/3 times 1/3, I get 2/9. So is that what actually happened here, though? When I did my tree diagram and I found the probability of having both of these things happening, probability of red on the first one and blue on the second one, it was only equal to 2/6. So these are not matching up, okay? Because these are dependent events. So I can't just multiply these two probabilities together, the probability of drawing A and the probability of drawing B, and multiplying them to get the probability of both of them happening, because these are not independent, they are dependent. Okay, let's see what happens if we try it with the rule for conditional probability. So the probability of A given B is equal to the probability of the intersection of A and B divided by the probability of B. Okay, so we said the probability of A intersecting with B, we said was 2/6. So the probability of A intersecting with B is equal to 2 out of 6. And the probability of just B happening all by itself, okay, the probability of B of drawing a blue marble is going to be 1 out of 3. So the probability of A given B should be equal to 2/6 divided by 1/3. Let's see what happens. So 2/6 divided by 1/3 is equal to 2/6 times 3 over 1, which gives me 2 times 3 is 6 over 6, which is equal to 1. And now, from our tree diagram, what did we say was the probability of A given B? We said that it's equal to 1. So the conditional probability formula still works for us if the events are dependent. The only thing that doesn't work for us is this formula right here. This one only works for independent events. So the probability of A and B only works if the two events are independent of each other. But in this case, the probabilities, the events, are dependent on each other. So how do we deal with this to make this a lot easier, rather than having to make a tree diagram every time and running through all these complicated situations? Okay, if two events are dependent, we cannot use the formula, the simple one, the probability of A times probability of B. So a tree diagram can be really useful, but there's another way of doing this. So instead, what we can do is we can just think about each draw. So think about the draws separately. So on the first draw, we want to get, what did we say, red on the first one? So first draw, we want red. And the second draw, we want blue. So what's the chance of getting red on the first draw? Well, on the first draw, there's 3 marbles in the bag, and 2 of them are red. Now, we're going to the second draw. Assuming we've already taken out a red one, because that's what we wanted. We got our red. That red is now gone. So how many marbles are left? There's 2 marbles left. How many of them are blue? Well, 1 of them is blue. And then if we multiply that together, 2 times 1 is 2, 3 over 2 is 6, and we get the same answer that we got by using our tree diagram. So this is the shortcut. This is the fast way. When you know your events are dependent, think about what you were left with after the first draw, and then you can set up your probability for the second draw. This works really well on theoretical situations, not so great on the situation that we did in class with the umbrella, the umbrella and the rain. That one was more complicated because each outcome was not equally likely. So things change a little bit. Okay, so this would be the probability of getting red on the first one and blue on the second one. But what if I changed this? What if I wanted the probability of getting red on both of them? So let's say I wanted the probability of red and red on the second one. So I'm kind of messing up my notation here, but let's just write this. Red and red. So the probability of red on the first one is 2/3. And then what's the probability of getting red on the second one? Well, there's still a red one in there, but there's only 2 marbles left. So that would be 2/6. Okay, now what about the probability of getting blue on the first one times the probability of getting red on the second one? Well, on the first draw, the probability of getting blue is going to be 1/3, because on the first draw there's 3 marbles, but only one of them is blue. And on the second draw, what's the probability of getting red? Well, I already took out the blue one, so there's 2 marbles left, and they're both blue. So what's the probability of that? Oh, again, I get 2/6. Okay, and the last kind of interesting question, what's the probability of getting blue and then blue again? Well, on the first draw, there's 1/3. And then on the second draw, there's no more blues. There's 2 marbles, but there's no more blues. So that ends up just being 0. It's impossible. And you can see it even works out with this kind of shortcut. Okay, so here's the first example that I did. This is similar to, this is a shortcut way of doing it rather than using the tree diagram. Okay, so now for your notes, we're going to do one really hard problem. Oops, and now it's time for 5th period. So you know what? The really hard problem, this guy right here, it's going to have to wait. We're going to do it together in class tomorrow. That's going to be our warm-up. So anyway, you have this. If you want to give it a try at home, good luck to you. And we will actually, though, do it in class tomorrow. So 4th period, I fixed math space. Go ahead and finish your math space assignment. 3rd period, not very many of you, only 25% of you, only 1/4 of you have done the math space assignment. So get on it. So finish your math space assignment. We'll do this in class tomorrow. Thank you.